Good morning, everyone. I'm Manish Jain, the founder and CEO of Dgraph Labs. Today, I'll be talking about high performance manual memory management in Go, why and how we use it in Dgraph. If you're unfamiliar with Dgraph, Dgraph is a horizontally scalable and distributed GraphQL database with a graph backend. Dgraph is designed to scale to terabytes of data, is fault tolerant, provides ACID transactions, and synchronous replication via Raft. It started as an open source project in 2015. In fact, we launched version 0.1 of Dgraph on December 3rd, 2015. So today marks the 5th year anniversary of Dgraph. In these 5 years, Dgraph has received some amazing traction with 5 million Docker pulls and 14,500 GitHub stars, and is ranked the #1 graph database on GitHub. We are really proud of that. But scaling to terabytes of data comes with pretty unique challenges. One of those have been managing memory with Go, a language with automatic garbage collection. The problem is, in garbage collected languages, memory allocations can outpace memory deallocations. The thing about dealing with a lot of data at breathtaking pace is that it requires the allocation of many small objects to hold the data in transient operations. And what do we know about allocating many small, short-lived objects in a long process? It leads to an increase in GC pressure. As you improve the performance of the program, it would do allocations faster, to the point where the speed of these allocations can outpace the speed of GC. And when GC is unable to keep up, it leads to out of memory. In other words, the faster the program runs, the more likely it is to go out of memory. Now, there are many tricks that we employ over the years to get memory in control. Avoid allocating on heap as much as possible, using sync.pool to reuse allocations, maintaining our own free lists, running GC more frequently. But still, we could not sufficiently solve the memory issues, and Dgraph kept running out of memory on heavy workloads. The issue was the allocation of Go structs. Wherever we had a lot of Go structs being allocated, we had significantly more memory issues. We didn't see the same issues when dealing directly with byte slices. And that provided the clue to two solutions, as we will see now. Solution number one is to keep data serialized. In other words, marshal a Go struct into a byte array. Conversely, avoid unmarshalling a byte array into a Go struct until you absolutely need to. Also, avoid putting lots of small objects into Go slices. Instead, serialize them individually and put them together onto bigger byte slices. This significantly decreases the memory pressure and allows you to allocate many objects fast and free them up quickly. Solution number two is to avoid Go GC. Allocate these byte slices manually outside the Go heap. So you can use them, you can free them as soon as you're done with them without waiting for a GC to happen, essentially bypassing the Go GC entirely. Now, this advice comes with a word of caution. Just like most Go users don't need to use unsafe or write assembly code, most Go users will never need to do manual memory management, and we would recommend against it. Having said that, for some of you who are crunching through a lot of data with Go and wishing for the kind of memory control that C or C++ can provide, this framework allows you to get that. I would go as far as saying that this is the missing holy grail that we at Dgraph have been looking for a while. So let's start with the manual memory allocation first. How do you allocate memory manually? The C standard library comes with Jmalloc and free. The Jmalloc function allocates memory for an array of n elements of size bytes each and returns a pointer to the allocated memory. The memory is set to 0 by default. Now, this is useful to avoid a Go bug when using C allocated memory. We implemented a wrapper over C's calloc function and returned a slice of bytes. This code is inspired by GoWiki talking about turning C arrays into Go slices. We also implemented a similar wrapper for free. These wrappers are quite handy for tracking down errors, as I'll explain later. To test the functions out, we created a small Go program to allocate lots of smaller memory chunks, adding up to 16 gigabytes of memory. Then we deallocated them until we only had 1 gigabyte of allocated memory left. And we repeated this cycle 30 times. The expectation was that the memory used would come down to 1 gigabyte after every cycle. But that's not what we saw. Unfortunately, we saw a lot of memory usage by the program. In fact, towards the end of the program, it held 20 gigabytes of memory, despite the program having freed every allocation. I know what you're thinking. No, it was not due to a memory leak, but it was due to a memory fragmentation, because standard libcalloc isn't thread aware, but Go uses threads and concurrency generously, so we needed a different solution. Enter Jmalloc. Quoting from the website, Jmalloc is a general purpose malloc implementation that emphasizes fragmentation avoidance and scalable concurrency support. Jmalloc first came into use as the FreeBSD libc allocator in 2005 and got a revamp in 2010 with heap profiling, monitoring, and tuning hooks. Overall, Jmalloc is well suited for a memory-intensive database program. And just to ensure we don't accidentally use the standard libcalloc, we prefix jmalloc library functions with je underscore. We also turned on some configuration options to deal with heavy workloads better. Now this is the calloc code using jmalloc's implementation of calloc. We replaced c.calloc call with c.je underscore calloc. We did the same for free. And it performed beautifully. With the memory allocation deallocation cycle test, the memory usage after every cycle came down to 1 gigabyte. And at the program end, Jmalloc was only holding 400 megabytes of memory, which is a small overhead. These functions allow us to allocate byte slices from Jmalloc, entirely bypass Go, and free them as soon as we are done without involving GC, with little memory overhead. Most importantly, it gives us predictable memory usage, which is crucial for memory-heavy programs. The second part of the equation is to lay out Go structs on byte slices. Now, there are multiple ways to do this. The most common ways are to use protocol buffers or flat buffers to marshal data. These are designed to allow future extensions of the data structures and be backwards compatible. These are great for long-term data storage, but their serialized formats are complex. The second option is to create Go types, which are in fact byte slices. These need handwritten serialization code, and we use functions to access their fields by parsing portions of the byte slice directly. This is sort of like flat buffers, but a lot simpler, and these are great for temporary data storage. And finally, we can take a normal Go struct, calculate its size using unsafe.size, and allocate that many number of bytes. Then cast them to unsafe.pointer to turn them into the struct type we want. This makes it easy to work with existing Go structs, but comes with certain caveats. First, memory has to be word aligned, which is easy. Second, while this works well for a freshly allocated memory from Go, you have to be careful around memory reuse with this technique. If reused, the memory needs to be sanitized carefully, and we are still investigating the best way to do so. You also need to be careful around referencing memory. It's important to ensure that calloc allocations do not reference Go allocations. because Go would not be able to track those references. Therefore, the Go GC could garbage collect them, which would then cause a seg fault. So you need to be very careful about how you reference your memory. Now that we have memory allocation figured out via Jmalloc and our data structures are laid out on byte slices, we have memory under control. But we do have some performance issues here because CGO is not Go. It introduces overhead for every C call. In fact, this overhead is quite significant. In this test, we allocated Go structs via Go versus via calloc. It is around 5 times slower. To deal with this, we created two libraries. Both are simple bump allocators in that they allocate bigger memory chunks and use them to lay out smaller byte slices and finally free them in one go. This amortizes the cost of CGO for memory allocation and freeing. The first is z.buffer, which is similar to bytes.buffer. In that, it grows by reallocating memory to twice the size of currently allocated memory. If the memory requirement increases, it can also auto map the data to a file to relieve memory pressure. Because the memory can be moved, all the references should be done via offsets. Z.buffer also has useful features like being able to recognize slice boundaries and iterate over them serially, and sort these variable length slices using merge sort algorithm. Note that the typical sort.slice would not work in this situation. The second is z.allocator. Z.allocator maintains an array of allocated byte slices. Each byte slice is twice the size of the previous one. It avoids reallocation, so it can be used to hold pointers to the allocated memory. Using these libraries, the cost of CGO is largely negligible. In this test, both Go and Z allocator took around the same amount of time to do all the allocations. In fact, all the manual memory allocations within Dgraph is being done via these libraries instead of calling z.calloc directly. So all of these discussions would not be complete without touching on memory leaks. Now that we are using manual memory allocation, there are bound to be memory leaks where we forget to deallocate memory. How do we catch those? I promised earlier to talk about the benefits of wrapping calloc and free calls. Let's look at them. One simple thing we did early on was to have an atomic counter track the number of bytes allocated via these calls. So we quickly know how much memory we have manually allocated in the program. If by the end of our program, we still had any memory allocated, this indicates a leak. When we did find a leak, we tried to use Jmalloc memory profiler, but that didn't see the entire call stack due to the CGO boundary. So thanks to runtime library, we were able to quickly build a simple system to capture the callers into z.calloc and match them against z.free calls. This automatically detects leaks and prints out the places where memory was allocated, but not freed. This can be turned on with the leak build flag. Let's showcase the power of z.buffer via a live demo. In this demo, what I'll do is I'll create a type map entry as I showcased before, which would be serialized by hand. And let's say this type map entry was part of an original struct, which had two fields. One is UID UID64 and a value, which is a byte slice. So instead of creating it in Go, we're going to have this as a serialized map entry. We would need a function to figure out the size of map entry given a val size, and the way we're going to format this is we're going to take 8 bytes for UID and the rest for val. So that would give us 8 plus val size. And We can marshal it given a val and a destination byte slice. And we do that by doing binary.pickindian.put uint64, and then we copy the rest into it. Then what we need is we need a way to get the UID back. And we need a way to get the value back. So we have that. Let's create a buffer. Create a buffer of a kilobyte. And let's write perhaps 1,000 map entries to it. So what we're going to do is we're going to get random sized values. We can say rand.int n, let's say 64. And this is our val size. We also create a temp buffer. This would add random bytes to the temp buffer, and we would allocate a slice of size map entry size given val size, which gives us the output. And then we can say map entry marshal to the output and give it a rand.63. Let's say 10,000, convert it to uint64, and the temp. So this would marshal a map entry into buffer directly. We did not allocate anything more. That's that. Now we have a buffer, a buffer which has around 1,000 map entries in it. Let's create a function to print out the buffer. Buff comes with a slice iterate, which will give us which would identify the slice boundaries and be able to give us a map entry. So we can say map entry s, and we can now print x comma me.uid me.val, and we need len. All right, and we return nil over here. And also what we'll do is we will just print out the numalloc bytes, which is the bytes used by calloc. And then print out the go heap. right? Okay. So and probably instead of using fump to printf, we should probably be using d.logf. Okay, that's better. And we'll do one more thing, which is that we are going to use now what we need to consider over here is that we have the map entries serialized over a big buffer, and it makes it trickier for us to sort over. So the buffer contains a sort slice function, which can give you these byte slices and sort using merge sort algorithm. So what we'll do is we'll say lm equals to map entry left, lr equals to, sorry, rm equals to map entry right. Actually, probably better to call it lme, rme, and then return lme.uid is less than rme.uid. And this would apply merge sort algorithm to sort them in place using half of extra memory compared to what we have in buffer. And now if we iterate the buffer again, we would be able to see these results in sorted order. Okay, let's try to see if we can run this. Oops, we are missing a return here. Okay, what else? Okay, let's run the test. So if you look carefully, we have 100 entries here, and the UIDs are they're not in sorted order. We used 0 Jmalloc bytes because we did not set the Jmalloc flag. But if you look after that, all these UIDs are in sorted order. This is after we ran the sort slice. Now let's run it with Jmalloc tag. And in this case, we now see that there is some memory allocated via Jmalloc. Now let's push it to the extreme and see the memory profile. So I'm going to change some settings here. We're going to make it to be 1,000,000, and we're going to make this temp to be 1 kilobyte. And yes, all right. Oops. UIDs are still in sorted order, and we see 1 gigabyte used by Jmalloc and 3.4 megabytes used by GoHeap. So let's look at what GoHeap is seeing. If we look over here, list test buffer, we see that the print buffer used up the 10 out of 27 megabytes. Print buffer used 10, and then another print buffer used 16. None of it was used by the actual buffer, even though we use around a gigabyte of memory. Go does not see that. Go only sees 27 megabytes of memory usage. So what we saw here is that we allocated 1,000,000 structs laid out serially over a bigger byte slice in z.buffer and completely bypassed the Go GC. And that concludes the demo. So now that we have figured out a way to manage memory and to figure out leaks, before I conclude the talk, I'd like to address some common questions that were asked on Reddit and Hacker News when the blog post came out. First was whether we ditched GoGC entirely. That's not the case. We only use manual memory management for memory-intensive sections. The rest of the code base is still allocating memory via Go and using GoGC. Secondly, why use Jmalloc? Why not allocate directly from the operating system? That definitely could be an interesting future project, but Jmalloc has been hardened over the past 15 years with the sole purpose of managing memory. Given our heavy memory needs, putting something rudimentary in place wouldn't work as well as Jmalloc. Also, Seago performance isn't a problem for us because of the libraries I mentioned earlier. And finally, why even bother with Go anymore? Why not switch to your favorite language? Now, every language, when pushed to extreme, comes with its own challenges. In fact, having now added manual memory management to our toolkit, Go has become even more amazing to use. So, in conclusion, memory management is a hard problem. Some languages take the problem completely away from you by doing everything with automatic garbage collection. And some languages put that entire problem on you by making it completely manual. But memory management does not have to be so Boolean. With these techniques, we get the best of both worlds. We can do manual memory allocation in critical memory bound code paths. At the same time, we can get the benefits of automatic garbage collection in non critical code paths. Even if you're not comfortable using Seago or Jmalloc, you can still apply these techniques on bigger chunks of Go memory with similar impact. All the core and libraries discussed in this talk are available in dgraph-io slash ristretto slash z package under Apache 2.0 license. So feel free to use them to improve memory management in your code base. Talking about hard problems, running distributed systems is hard. And that's why we are launching Slash Enterprise. Slash Enterprise is hosted Dgraph. It's deployed in your cloud and managed by us. We handle the complexity of running distributed, scalable Dgraph for you, and you handle scaling your business. Slash Enterprise is the easiest way to get a scalable GraphQL up and running with terabytes of graph data. You get all the benefits of Dgraph's high availability, Jepson tested distributed ACID transactions, and fault tolerance without any of the operational headaches. In fact, for any of the conference attendees, to get a taste of Slash Enterprise, we are giving away 3 months of Slash GraphQL free. You can use the code GSC2020 to activate your free 3-month trial on slash.dgraph.io. And finally, thank you for attending this talk. This talk is based on a similarly titled blog post, which you can read in the link here. We put together this conference because we wanted to have a dedicated venue for talking about building and scaling systems in Go. And thanks to our team, we have put together a lot of great talks for you today. So hope you enjoy the conference and see you again later in the day for Q&A. Thank you.